It is possible that quite a number of people have not come across the Rotoverter system, so here is some basic information on it. The Rotoverter system uses a standard three-phase electric motor. A three-phase motor has got three windings, each of which is powered up sequentially to provide rotation of the output driveshaft. It is possible to change the wiring of such a motor so that the input power drives only one of the three windings, leaving the other two windings for output power. This circuit has been presented as a public domain, non-copyrightable circuit by Hector Perez Torres. The Rotoverter has been reproduced by several independent researchers, and it produces a substantial power gain when driving devices which need an electrical motor to operate. Typically, the input power requirement is cut to just 10% of the original power needed. For example, it is possible to power a rotoverter with a solar panel and use the rotoverter to pump water from a well. However, the greatest interest is in generating an electrical output. One method of arranging it is shown here. You've got the AC mains, which feeds to the motor, along with two capacitors, which will be discussed later. There's a coupling between the rotoverter motor and an alternator. The alternator has got three phases in its output power, which with either a special single block device or 6 separate diodes can then give a DC electrical output from the input provided on the turning of the alternator shaft. The output device is usually an alternator. It's driven by a three-phase mains powered 3 horsepower to 7.5 horsepower motor. Both of these devices can be standard asynchronous squirrel cage motors. The drive motor is operated in a highly non-standard manner. It is a 240 volt motor with 6 windings, as shown below here, and the input voltage for the motor should always be a quarter of its rated operational voltage. A virtual third phase is created by using a capacitor which creates a 90-degree phase shift between the applied voltage and the current. The arrangement needs a different value capacitor when starting as compared to when the motor is running normally. The best capacitor size for any particular drive motor has to be determined by experiment with that particular motor. A capacitor switching box can be very helpful because you're going to put an extra capacitor across the run capacitor that's there all the time the motor is running. The capacitor shown here can produce any value from a half a microfarad to 31.5 microfarads, and it can be rapidly switched to find the correct resonant value for your particular motor. These values allow combined values of 0.5, 1.0, 1.5, 2.0 and so on by selecting the appropriate switches to be on or off. Should you need a value greater than this, then wire a 32 microfarad capacitor in place permanently and connect the substitution box across it so that you can test higher values step by step to find the optimum value of capacitor to use. The capacitors need to be powerful, oil-filled units with a high voltage rating. In other words, large, heavy and expensive. The power being handled in one of these systems is large, and setting one up is not without a certain degree of physical danger. These systems have been set to be self-powered, but this self-powering is not recommended, presumably because of the possibility of runaway, with the output power building up rapidly and boosting the input power until the motor burns out. The Yahoo EV Grey group, which is shown with this link here, has many members, and many of those are very willing to offer advice and assistance. A unique jargon has built up on this particular forum, where the motor is not called a motor but is referred to as a prime mover, or PM for short, which can cause confusion as PM usually stands for permanent magnet, not to mention Prime Minister. Rotoverter is abbreviated to RV, while DC PM RV stands for Direct Current Permanent Magnet Rotoverter, and TRAFO is a non-standard abbreviation for transformer. Some of the postings in this group may be difficult to understand due to the highly technical nature and the extensive use of abbreviations, but help is always available on that particular group. To move to some more practical construction details for the system, the motor and alternator considered to be the best for this application is the Baldor EM3770T 7.5 horsepower unit. Specification number is 07H002X790, and it is a 230 to 460 volt 60 Hz 3-phase 19 or 9.5 amp 1770 RPM with a power factor of 0.81. The Baldor website is www.baldor.com, and the following details should be considered carefully before trying any adaptation of an expensive motor. The following constructional photographs are presented here by kind permission of Ashworth of the EV group, the EV Grey group. The end plate of the drive motor needs to be removed and the rotor lifted out. Considerable care is needed when doing this, as the rotor is heavy and it must not be dragged across the stator windings, because if you do that you will damage them. So you have to support the weight of the rotor as you lift it out of the housing. The other end plate then is removed and placed on the opposite end of the stator housing. This arrangement is to switch the innards of the motor around, so that what was the front end now becomes the back end. The fan is removed as it's not needed, and it just causes unnecessary drag, and the rotor is inserted in the opposite way round to the way that it was removed. That is, the housing is now the other way round relative to the rotor. Since the rotor has been turned through 180 degrees before being replaced. The same part of the shaft of the rotor passes through the same end plate as before, as the end plates have also been swapped over. The end plates are bolted in position and the rotor shaft spun to confirm that it still rotates freely as before. Well, as freely as before. To reduce friction to an absolute minimum, the motor bearings need to be cleaned to an exceptional level. There are various ways of doing this. One of the best is to use a carburetor cleaner spray, which you can get at your local car accessory shop. Spray inside the bearings to wash out all of the packed grease. The spray evaporates if left for a few minutes. Repeat doing this until the shaft spins perfectly, and then put one, and only one, drop of light oil on each bearing, and don't use WD-40 as it leaves a residue film. The result should be a shaft which spins absolutely perfectly. The next step is to connect the windings of the two units. The motor, so-called prime mover, is wired for 480 volt operation, This is done by connecting the winding terminals 4 to 7, 5 to 8 and 6 to 9 as shown here. If this motor were operated in the standard way, a 480 volt three-phase supply would be connected to terminals 1, 2 and 3, and there'd be no capacitors in the circuit. It's suggested that the jumpering of the motor windings is more neatly done by removing the junction box cover and drilling through it to carry the connections outside to external connectors, jumpered neatly to show clearly how the connections have been made for each unit, and to allow easy alterations should it be decided to change the jumpering for any reason. The result of doing that looks like this. You have your motor as before, and then the jumpers are carried outside so that you can see exactly what way it has been jumpered. The same is done for the unit which is to be used as the alternator. To increase the allowable current draw, the windings inside the motor are connected to give the lower voltage with the windings connected in parallel, as shown here, with terminals 4, 5 and 6 strapped together, 1 connected to 7, 2 connected to 8 and 3 connected to 9. This gives a three-phase output on terminals 1, 2 and 3, and this can be used as a three-phase AC output, or alternatively as 3 single-phase AC outputs, or as a DC output by wiring it as shown here, which is where you pass the AC of each winding through to a capacitor and diode. The motor and the alternator are then mounted securely in exact alignment and coupled together with a standard inline connection. The switching of the direction of the housing on the drive motor allows all of the jumpering to be seen on the side of the two units when they're coupled together facing each other. The input drive may be from an inverter driven from a battery, and the battery can be charged via a solar panel. The system now needs to be tuned and tested. This involves finding the best starting capacitor, which will be switched into the circuit for a few seconds at startup, and the best running capacitor value. That's the capacitor which will be in place all the time that the motor is running. To summarize, this device takes a low power 110 volt AC input and produces a much higher power electrical output, which can be used for powering much greater loads than the input could power. The output power is much higher than the input power. This is free energy under whatever name you like to apply to it. One advantage which should be stressed is that very little in the way of construction is needed, because you're using off-the-shelf motors and no knowledge of electronics is actually needed, which makes this one of the easiest to construct free energy devices available at the present time. One slight disadvantage is that the tuning of the prime mover motor depends on its loading, and most loads have different levels of power requirement from time to time. A 220 volt AC motor can also be used if that is the local supply voltage. It's not essential to construct the rotoverter exactly as shown above, although that's the most common form of construction. The Muller motor can have a 35 kilowatt output when precision constructed, as Bill Muller did. One option therefore is to use one Baldor motor jumpered as the prime mover, drive motor, and have it drive one or more Muller motor style rotors to generate the output power. So the output shaft is coupled to a drive shaft which spins in this case, two rotors between their stator pickup coils. T.J. Chorister in America has used a rotoverter style circuit for some time now. He uses a 200 volt 3-phase electric motor driven by a single phase 120 volt 60 Hz main supply. He says the hot wire goes directly to one phase. It also goes through a run capacitor to the second phase, also through an inductor to the third phase. You have to experiment with the values of the capacitor and inductor in order to get the smoothest running of the motor. Often you will not even need a switch starting capacitor. Generally, a 1 horsepower motor will output about 3/4 of a horsepower. However, the arrangement will be much more efficient than a single phase motor. The neutral is not needed, but be sure to use a ground connection to the frame of the motor. Run capacitors pass about 1 amp for each 22 microfarads of its capacity, so they act as current limiters when in series in an AC circuit. Inductors should have wire which is thick enough to carry the current needed by the motor. I have no guidelines for inductors, he says, so just try it. If you can measure one leg of the motor winding, then that would be about right for the inductor. The inductor value is adjusted by trial and error until you find the value where the motor runs most smoothly. If a starting capacitor is needed, then just parallel a starting capacitor and switch and connect a bleeder resistor to the run capacitor. The circuit, he says, is like this. You have the 3 windings of the motor connected in a delta form. You've got an inductor across one, you've got a capacitor across the other, and the input is through the normal supply line here. 120 volt AC is coming through. Phil Wood has many years of experience working with all varieties of electric motor, and he's come up with a very clever circuit variation for the rotoverter system. His design has a 240 volt prime mover motor driven with 240 volts of AC. The revised circuit now has automated startup, and it provides an extra DC output which can be used to power additional equipment. His circuit is shown here. You have the windings of the motor connected in series as before, with the 240 volt AC input. You've got the capacitor there, another non-polarized capacitor here, diode bridge in 2 positions, and the starting run capacitor with its bleed resistor in that particular position. Phil specifies the diode bridges as being 20 amp 400 volt, and the output capacitor is 4000 to 8000 microfarads at 370 volt working. The on-off switch on the DC output should be 10 amp 250 volt AC working. The circuit operates as follows. The charge the charge capacitor C which is there needs to be fully discharged before the motor is started, so the press button switch is pressed to connect the 1K resistor across the capacitor to discharge it fully. If you prefer, the press button switch and resistor can be omitted and the switch to the DC load closed before the AC input is applied. The switch must then be opened and the AC connected. The starting capacitor S, which is there, and capacitor R, which is there, both operated at full potential until capacitor C begins to charge. As capacitor C goes through its charging phase, the resistance to capacitors R and S increases, and their potential capacitance becomes less, automatically following the capacitance curve required for proper AC motor operation at startup. After a few seconds of runtime, the output switch is operated, connecting the DC load, which is there, that's the switch we're talking about here, and by varying the resistance of the DC load, the correct tuning point can be found. At that point, the DC load resistance keeps both of the capacitors R and S operating at a potentially low capacitance value. The operation of this circuit is unique, with all of the energy which is normally wasted when the AC motor is started being collected in the output capacitor C. The other bonus is where a DC load is powered for free, while it keeps capacitors R and S in their optimum operating state. The DC load resistance needs to be adjusted to find the value which allows automatic operation of the circuit. When that value has been found and made a permanent part of the installation, then the switch can be left on when the motor is started, which means that it can be omitted. If the switch is left on through the starting phase, capacitor C can be a lower value if the DC load resistance is high enough to allow the capacitor to go through its phase shift. The capacitor values shown above were those found to work well with Phil's test motor, which was a 3-winding 5 horsepower 240 volt unit. Under test, driving a fan, the motor draws a maximum of 117 watts, and a variable speed 600 watt drill was used for the DC load. The motor operates at its full potential with this circuit. The circuit will need different capacitors for operation with 120 volt AC supply. The actual values are best determined by testing with the motor which is to be used, but the following diagram is a realistic starting point, and that's because it specifies the values of the components that are being used in the circuit. Now that's for a 120 volt AC input. The 120 volt AC motor runs very smoothly and quietly, drawing only 20 watts of input power. Advancing the design even further, Phil has now produced an extremely clever design by introducing an additional DC motor generator coupled to the prime mover. The coupling is nominally mechanical, with two motors physically linked together with a belt and pulleys, but the electrical linking is such that the two motors will synchronize automatically if the mechanical linkage is omitted. I'd like to express my thanks to Phil for sharing this information, these diagrams and photographs quite freely. This is Phil Wood's final circuit on this sort of arrangement. This circuit is very clever, as the DC motor generator automatically adjusts the running of the AC motor both at startup and under varying loading. Also, the section and selection of the capacitors is not so critical, and no manual intervention is needed at startup. In addition, the DC motor generator can be used as an additional source of electricity. This is a photograph of Phil's actual physical setup. As the loading on the drive motor is quite low due to the very high efficiency of the rotoverter arrangement, it is perfectly feasible to drive the whole system with a low power inverter run from a battery. If that is done, then it's possible to use two batteries. One is charged by the DC generator, while the other is driving the inverter. A timer circuit then switches the batteries over on a regular basis using relay switching. We got the possibility, though, of extra energy collection. A very effective additional circuit has been developed by David Kousaloudis. This circuit allows extra current to be drawn off a rotoverter while it's running, without increasing the input power needed to drive the rotoverter. David's circuit can be used with a wide range of systems, but here it's being shown as an addition to the rotoverter system, raising its efficiency even higher than before. As is common with many effective circuits, it is basically very simple looking, and its apparent operation is easily explained. The objective is to draw additional current from the rotoverter and use that current to charge one or more batteries without loading the rotoverter at all. The current takeoff is in the form of a rapid series of current pulses, which can be heard as a series of faint clicks when fed into the battery. Let's examine the circuit section by section. First, we start with a standard off-the-shelf three-phase motor. In this example, the motor is a 7.5 horsepower motor, which, when wired in rotoverter mode, using just a single phase supply as shown here, only draws a very low amount of power when running, especially if the single phase supply is about 25% of the voltage rating of the motor. Because the running power draw is so low, it's possible to run this motor from a standard battery-powered inverter, but the current draw at startup is some 17 amps, so the mains is used to get the motor started, and then the motor is switched from the mains to the inverter. The inverter also allows easy measurement of the power input, and so makes for an easier calculation of the overall power efficiency of the system. There is a power extraction device called a diode plug, which, in spite of its seeming simplicity, is actually much more subtle in its operation than would appear from a quick glance of the circuit. This is the diode's plug circuit here. This circuit is being presented as a public domain, non-copyrightable circuit by Hector Perez-Torres, and is capable of extracting power from a range of different systems without affecting those systems or increasing their power draw. In this circuit below here, just the first half of the diode plug is used, although it should perhaps be stressed that it would be perfectly feasible to raise the efficiency of the circuit even further by adding extra components to duplicate the power feed from the battery, drawing on both parts of the diode plug circuit. For clarity, this is not shown here, but it should be understood that it is possible, and indeed desirable, extension to the circuitry described here. When the motor is running, high voltages are developed across the windings of the motor. As only the first half of the diode plug is shown here, we will be capturing and using the negative going voltages. These negative going pulses are picked up, stored in a capacitor, and used to charge a battery using this particular circuit here. Here we have the same rotoverter circuit as before, with high voltage being developed across capacitor C1, which is here. The battery charging section is a free-floating circuit connected to point A of the motor. That's point A there. The high voltage diode D1, which is here, 1N5408, is used to feed negative going pulses to capacitor C2, which causes a large charge to build up in that capacitor. The appropriate moment, the PC851 opto-isolator is triggered. This is the opto-isolator here. When it's triggered, it switches on and feed current into the base of the 2N 3439 transistor. The transistor switches on as a result of that, and it fires the thyristor or SCR, the 6509 type. It effectively switches capacitor C2 across the battery, being here, and this discharges the capacitor into the battery. This feeds a substantial charging power pulse into the battery. As the capacitor voltage drops, the thyristor is starved of current and it turns off automatically. The charging sequence for the capacitor starts again with the next pulse from the windings of the motor. The only other thing to be arranged is the triggering of the opto-isolator. This should be done at the peak of a positive voltage on the motor windings and has been built like this. Here we have the rotoverter motor as before, with the voltage developed on C1 being used to trigger the opto-isolator. It's done by passing through D2 to a voltage level setup controlled by the turns of this preset. That feeds it back through to the neon and on through the 1K resistor to the LED part of the particular opto-isolator. And you adjust the 10-turn preset here so that the neon fires at the peak of the voltage wave coming from the motor. Although the adjustment screw of most preset resistors is fully isolated from the resistor, it is recommended that adjustment of the screw be done using an insulated mains tester type of screwdriver or a solid plastic trimmer core adjustment tool. The circuit to test one half of the diode plug is then this, which is the first diagram and the second diagram combined together. The switch SW1, which is here, is included so that the charging section can be switched off at any time, and this switch should not be closed until the motor gets up to speed. All wire connections should be made before the power is applied to the circuit. Capacitor C1, which is shown as a 36 microfarad, has a value which is optimized for the particular motor being used and will normally be in the range of 17 to 24 microfarads for a well-prepared motor. The motor used for this development was retrieved from a scrapyard and was not prepared in any way. As said before, please understand that the capacitors we're talking about here are oil-filled types. They're large, they're heavy, and they're expensive. The value of capacitor C2 can be increased by experimenting to find at what value the resonance gets killed and the charging section starts drawing extra current from the supply. It should be noted that many new thyristors, silicon controlled rectifiers or SCRs, are faulty when supplied. Sometimes as many as half of those supplies can be faulty. It's therefore important to test the thyristor to be used in the circuit before installing it. The circuit shown below can be used for the testing, but it should be stressed that even if the component passes the test, that does not guarantee that it will work reliably in the circuit. For example, while 2N6509 thyristors are generally satisfactory, it has been found that C126D types are not. A thyristor passing the test may still operate unpredictably with false triggers. Please note that the 2N6509 package has the anode connected through to the metal mounting tab, which is part of the heatsink arrangement. the components list for this lot of components here is shown with their particular specifications. When using and testing the circuit, it's important that all wires are connected securely in place before the motor is started. This is because high voltages are generated, and creating sparks when making connections does not do any of the components any particular good. If the circuit is to be turned off while the motor is still running, then switch SW1 is there for just that purpose. The operating technique is as follows. Before starting the motor, adjust the slider of the preset resistor VR1 to the fixed resistor end of its track. This ensures that the charging circuit will not operate, as the neon will not fire. Power up the circuit and start adjusting the preset resistor very slowly until the neon starts to flash occasionally. There should be no increased load on the motor, and so no extra current draw from the input supply. If there is an increase in the load, you'll be able to tell by the speed of the motor and the sound that it makes. If there's an increase in the load, then back off VR1 and check the circuit construction. If there's no increased load, then continue turning VR1 slowly until a position is reached where the neon remains lit all the time. You should see the voltage across the battery being charged increase without any loading effects on the motor. If you use an oscilloscope on this circuit, please remember that there is no ground reference voltage and the circuit is not isolated. Here's a picture of David's actual board construction. There are various ways for building any circuit. This particular construction method uses plain matrix board to hold the components in position, and the bulk of the interconnections are made underneath the board. The charge collecting capacitor is made here from two separate polypropylene 440 volt capacitors wired in parallel. David has opted to use a separate diode on each capacitor, as this has the effect of doubling the current carrying capacity of a single diode, and it's a popular technique in pulse charge circuits where sometimes several diodes are wired in parallel. David has included a heatsink, which he marks as being not required, but you'll notice that there is insulation between the SCR and the heatsink. Mica washers are so called, are available from the suppliers of semiconductors, and they're particularly good for this because mica is a good insulator of electrical current, and it also conducts heat very well. Phil Wood has developed a particularly effective method for extracting the excess resonance circulating energy of a rotoverter prime mover, and this is the circuit here. Care needs to be taken when constructing this circuit. For example, the circuit performance is displayed by an AGF 4017B 5-stage Johnson counter, but for some lunatic reason the 4017 designation is also used for a completely different chip of the same size and number of DIL pins, namely the CMOS high-speed hex flip-flop with reset. An action definitely worthy of a stupidity award. Another point to watch out for is that the 1 amp 1N5819 diode is a very high speed Schottky barrier component. The operation of the circuit is as follows. The input from the rotoverter motor is stepped down by a transformer to give an 18 volt nominal AC output, which is then rectified by a standard rectifier bridge and the output smoothed by an 18 volt Zener diode and a 330 microfarad smoothing capacitor, and used to power the MC34151 chip. This DC power supply line is further dropped and stabilized by a 15 volt Zener diode and a 47 microfarad capacitor, and it's used to power the LED display chip HEF 44017B. The rotoverter input is also taken direct and rectified by a second 400 volt 35 amp rectifier diode bridge and smoothed by a 20 microfarad capacitor with a high voltage rating. It must be understood that the rotoverter system is liable to produce considerable power surges from time to time, and so this circuit must be capable of handling and benefiting from these surges. This is why the IRG 4PH 440UD IGBT device was selected, apart from its very reasonable price, as it is robust and can handle high voltages. The resulting high voltage DC is taken by the chain of components, two 75 volt Zener diodes, 20k resistor and 100k variable resistor. The voltage developed by the slider of this variable resistor is loaded with a 10k resistor and voltage limited with a 10 volt Zener diode and decoupled with a 10 nanofarad capacitor before being passed to the MC34151 high-speed MOSFET dual driver chip. Both of these drivers are used to sharpen up the pulse and drive the IGBT cleanly. The result is an output which is a series of DC pulses. The operation of the circuit can be seen quite clearly thanks to the HEF 4017B display circuit, which drives a row of LEDs triggered by the IGBT gate signal, divided by the 1K 4.7K voltage divider and decoupled by the 10 nanofarad capacitor. The display shows clearly when the IGBT is switching correctly. Actually, the display circuit is quite a useful device for people who do not own an oscilloscope, not just for this circuit, but for a wide range of different circuits. The physical board layout for Phil's circuit is shown below, and as you will notice from the notes on Phil's board layout, the first 75 Zener diodes used on the direct rotoverter power feed should be replaced by a 30 volt Zener if a 120 volt motor is used in this circuit. This is the layout of his circuit, and you can study that from the accompanying document. Another important point which needs to be stressed is that the pulse DC output from this circuit can be at extremely high voltages and needs to be treated with considerable care. This is not a circuit for beginners, and anyone who's not familiar with handling high voltages needs the supervision of an experienced person. Also, if either this circuit or the rotoverter is connected to the mains, then no scope ground leads should be connected, as the circuit can be 100 volts or more below ground potential. This is the PCB board if you want it, and this is the packaging of the components for the circuit that's as described so far. That is the circuitry and connections for the MC34151 chip. This is what his particular build looked like, and this is a list of the components used in this particular design.